Section 3.7 is implicit differentiation. So we're continuing our differentiation rules. A lot of words here. Let's read through them and write down what you need to. An important problem in calculus is how to find the slope when the function can't conveniently be solved for y. Instead, y is treated as a differentiable function of x with both sides of the equation. And both sides of the equation are differentiated with respect to x using the appropriate rules, sums, products, quotients, chain rule. Then we solve for dy dx in terms of x and y together to obtain a formula that calculates the slope at any point xy on the graph. So again, what we're talking about here is a function that cannot be written as a function because at some point, and it may be something like this, for any given x, there may be one more point or one more place where the slope can be calculated. So we need to have a point xy on the graph rather than for most differentiation we can find a derivative at any point for x. This process is called implicit differentiation, and the phrase derives from the fact that the equation, for example, x cubed plus y cubed minus 9xy, defines the three separate functions implicitly, for example, hidden inside the equation without giving us explicit formulas to work with. So implicit rather than explicit. So here's an implicit function. And I misspoke back here. These are not our F1, F2, F3s. My bad. So they've split into three functions. So the blue function, the black function, and the red function. Notice that all three of these together would not form actually a function because it doesn't pass the vertical line test. But if we split it, we can have this kind of notation where we can get a slope at any point. So let's do this. Find dy dx if 3y squared plus 2y equals 5x. So first find dy dx by differentiating both sides. Now in this, since we're deriving dy with respect to x, then anytime we are differentiating a y variable, we need to use the chain rule. So using the product rule for the first, power rule, we bring down the 2, we get 6 times y. Since we're derivating with respect to x, we need dy dx plus 2 dy dx equals 5. Since we're differentiating with respect to x again, dx would just be 1, the derivative of x with respect to x. So you can see how they did each piece separately here. And then factoring out dy dx, and finally dividing both sides by 6y plus 2. Notice that the derivative here ended up being just in terms of y, which means that all of our slopes for various y's are the same irregardless of x. So the basic steps: differentiate both sides with respect to x, collect the dy terms on one side, factor out dy dx, and solve for dy dx. Okay, again, in the law that describes how light changes direction as it enters the lens, the important angles are the angles of light that make the line perpendicular to the surface at every point of entry, the normal line. So this is what we're looking at. So when we've got a curve and we're looking for a normal line, typically something that's really important for lenses, any kind of parabolic curve, satellite dishes, things like that. So talking about the normal line here and the tangent line. So find the equations of the tangent and normal lines to this graph at this point. So first of all, we are going to go ahead and differentiate. So take a moment, find the derivative, and then turn the screen back on and see how you did. Okay, so the first one is 4x cubed. There is no y term, so I don't need to put any y primes in. Then using our product rule, derivative the first times the derivative of the second, there's your implicit inside chain rule, plus the derivative of the first times the second, no need for any derivation of y there, minus, and then again, power rule 2y dy dx equals 0. So again, using that x squared y squared as a product, which would be this portion here. Whoops. Yeah. All right. Continuing on, factoring out everything that has a dy and moving anything without a dy to the opposite side, and then solving for dy dx. So if you got this as your final answer, well done. If not, take a look and see where you went wrong. Now, we want the normal and the tangent line at this point. So the first thing to do is to find our slope at this point. Oh, I'm sorry, they simplified it a little bit further there, canceled the 2's. Okay, so find the slope. So go ahead and try that. Plug in your root 2 over 2. I'm a root 2 over 2. So a lot of work there, but we get down to the slope is 3. So that's the slope we're going to use for our tangent line. That's the slope at the point of the curve. So the tangent line, using this as my xy point, y minus y sub 1 equals 3 times x minus x sub 1, and then simplification. To do the normal line, we are going to use the slope of negative 1/3. It's perpendicular. So tangent lines, normal line. And second derivative, so again, let's try this. Look for the first derivative for me, and then come back. So there's our first derivative. This is a derivative that you might want to memorize. This is any circle centered at 0, 0. Since the radius is a constant, it makes absolutely no difference in the derivative. Any circle, no matter how big the radius, at any point on the circle, the slope is, if that's xy, the slope at any point is negative x over y. So just keep that in mind, and this might be one that would come in handy to know without having to go through the process. Then to find the second derivative, differentiating again with respect to x. So again, pause and find the second derivative on your own. So using the quotient rule and our implicit differentiation, dy dx, we already know what it is. We're going to substitute that in, continuing to simplify, and we get this as our second derivative. So hopefully you did well on that, and that's it.